The following program is brought to you by Caltech.
Good morning. Welcome back. I'm going to get us started back again and keep us somewhat on track today. I'm very, very pleased that we have a number of members of the Caltech community here who have agreed to talk with us about campus sustainability and some of the efforts that are going on campus. Jim Cowell joined Caltech as the Associate Vice President for Facilities in October of 2007. He's responsible for campus facilities, utilities, capital improvements, sustainability, and facilities services, including safety, security, emergency preparedness, faculty housing, and graphic resources and mail services. The Caltech campus is comprised of 125 acres and 4 million square feet of buildings. So he's got quite a substantial responsibility here. And prior to Caltech, Jim was the LA Unified School District, was with the LA Unified School District from 2004 to 2007, where under his leadership, the $12 billion new school building program was on track to build 150 new schools through the district by 2012. So I'm sure they missed his leadership in that regard. Jim comes to us with experience from the Civil Engineering Corps of the United States Navy, and he most recently commanded the Naval Construction Battalion Center at Port Hueneme, and I'm sure I've pronounced that completely wrong, where he was, thank you. I'm not going to try again. He was responsible for the mobilization, logistics, and training of thousands of Seabees deployed around the world in the global war on terror. Jim earned his bachelor's degree from the University of Florida and a master's degree from MIT in both in civil engineering. He's a registered civil engineer in California. And also with us is John Onderdonk, who serves as the manager for sustainability programs at Caltech, where he's developing and managing programs to improve environmental performance in the areas of energy, climate, water, waste, supply chain, transportation, and building infrastructure. Prior to joining Caltech, John worked in the environmental risk management field, serving as the Southwest Regional Manager for AIG Environmental, where he developed liability transfer programs for brownfield redevelopment clients. He's also worked as an environmental consultant, helping corporate clients integrate sustainability into their business practices and to address environmental regulations. John holds a master's in corporate environmental management from the Donald Bren School of Environmental Science and Management at University of California, Santa Barbara, and a bachelor's of science in environmental science from the University of Oregon. John's a certified carbon reduction manager and a LEED accredited professional, and Caltech is very fortunate to have him helping us with our sustainability program. And with that, I'll turn it over to John, and he can talk about what's going on.
All right. Thank you very much. Thank you all for having me here. We've got a lot of ground to cover, but we'll jump right in. And as you heard, we have a lot of sustainability initiatives on campus covering water and transportation and buildings and all sorts of things. But we're going to focus today on our energy initiatives and greenhouse gas mitigation initiatives because, as you've heard over the prior sessions, energy is the most fundamental challenge that we face. And so it's important that the facilities department and the campus operate in a way that is recognizing those challenges and providing mitigation measures to address those. It's also critical that we do sustainability initiatives that are supportive of the core mission of the Institute. We're not here to be green just for the sake of being green. Education and research is our primary mission, and all of our sustainability initiatives that we have implemented and that you'll learn about today support that core mission. And that's a critical component because clearly we want to support the research that's going on here. So let's start the story by looking at our energy overview, the historic energy consumption on campus. You can see that there's a steady growth going up over the years. The blue section here is the energy we consume from the city of Pasadena. The orange section above that is the energy we generate on campus with our cogen system. It's a 12.5 megawatt natural gas turbine. And then you can see a tiny little sliver up there of yellow. Those are our new solar photovoltaic panels that are contributing to the energy generation as well. But the overall theme here is that there are three main drivers behind our efforts to incorporate sustainability, particularly on the energy side. The first is obviously this growth here of energy consumption, and it's related to this point here of energy intensity. When you look at our campus, we have an energy intensity of about 300 MBTUs per square foot. To put that in perspective, the typical UC school, the average UC campus, is about 180. And all those UC campuses are significantly larger than we are. So what that means is that that's what makes Caltech unique. The fact that we have research here, and every one of our buildings is a research laboratory. That's what makes Caltech special, and we want to support that. Our initiatives are here not to switch to a liberal arts school. We want to make sure that we maintain our focus on research and the cutting edge research that we do. So that's a challenge for us. We need to support that mission, but do it in a way where we can be a little bit more energy efficient, a little more cognizant of where we get our energy. The second point is that obviously all this energy costs us a lot of money, and that's money that doesn't go to the core mission of teaching and education and research. So, we're working on that problem. We started out in 2009 with a budget of about $20 million. Over the subsequent years, we've knocked that down now to projected 2012 figures of $15.5 million. So that's good news. We're on the right track. The other really important thing to point out here is this $1 million in project repayments. In a minute, I'll describe how we're funding all of our energy conservation measures, but essentially what that means is that we have $1 million in FY11 that is coming back as savings from our utility budget that's coming back to the Institute as a benefit. So again, we're not only reducing the overall spend, but we're generating a return for the Institute. The final component and driver that we're looking at is greenhouse gas emissions. We started back in 2008 looking at our campus-wide greenhouse gas emissions and understanding what we could do to reduce those. It's pretty clear when you look at the slice of the pie here in 2010 that about 75% of our emissions come from the energy that's consumed in our buildings, either the energy that we purchase or the energy we generate on campus. So it's clear that the buildings is where we need to focus and put our energy, so to speak, on reducing our energy consumption. We have in the last year seen have sort of a roughly 5,000 metric ton reduction from 9 to 10. So we are improving, and then we're anticipating that as these energy efficiency projects kick into place, we will have more significant savings on our way to achieving our 2020 goal of reducing our carbon emissions to the 1990 levels. So I mentioned we'll talk about how we're funding our projects. And we have developed a program called the Caltech Energy Conservation Investment Program. Essentially what that is a green revolving fund where we are borrowing money from the endowment, a portion of the endowment that was earmarked and set aside for energy conservation measures and other capital improvements. We're borrowing money from that to fund the initial energy conservation measures, and then the utility savings from those conservation measures are being plowed back into the endowment as a return. And you can see that we have three critical components of this system. Without these three components, the payback wouldn't work. Every project that we do has to have verifiable savings. We have to be able to document that a project saved a kilowatt hour or X number of kilowatt hours, and that it's tied to a dollar savings. That's absolutely critical. We also want to make sure that there's a plan for measurement and verification ongoing. We don't want to implement an energy conservation project and pat ourselves in the back and walk away, only to have that project deteriorate or the building energy go back up to its steady state, and then we've lost all of our savings and energy conservation efforts in the interim. So it's very important that we measure and maintain that savings as we go through the life of the project, well beyond the initial payback of that loan. And the last is that we are constraining our paybacks to 6 years. That was a simple measure for us to make sure that we are having a positive return to the endowment and giving them a real value for their money. And you can see in the bottom chart here some of the numbers we've achieved. And as I mentioned, we've had about $1 million in savings in this last year come back to the Institute. That's about 10 megawatt hours of energy consumption that we've cut from our demand. This is a graphic that shows the individual projects on a quarterly basis, the paybacks. What's important here is really the nice upward curve. We're saving more. We're also getting more diverse in the number of projects we have in each of the quarters. So that's also a good thing. We're getting more complicated. We're hitting more of these projects than we were initially. So on average, right now, we're averaging about $250,000 a quarter in returns to the endowment. The very first project that we implemented with the CECIP program was an LED lighting retrofit in our South Wilson and North Wilson parking garages. We chose this project because it was a relatively simple lighting swap out. It was relatively low cost, about $25,000 in initial cost. We received a significant rebate and had $9,000 in avoided costs, so it was really a no-brainer from an economic standpoint. It really gave us that ability to track that savings and show the administration and the financial group and the endowment group that we could actually track this savings, and it was real. We've moved on to more complicated projects, and as we go on and we become more adept at these. This is an example of the lighting projects we have implemented across campus. About more than half of the campus is undergoing or has undergone a lighting upgrade, saving almost a megawatt of energy. And that's important to note when we talk about our renewable generation portfolio, because if we didn't hit these savings on the energy efficiency side, we would essentially negate all of our energy that we're generating from our solar arrays. And again, significant dollar savings to be had. We've gone from the lighting to look at all of the building systems, and it's a process we call retrocommissioning. The simple definition is to optimize the building system performance. Essentially, we're looking at the mechanical systems in the building, the chilled water, the hot water, and looking at ways that we can improve those buildings and bring them back up to their standard of how they were meant to be operated. And in some cases, taking those buildings and going beyond the way they were meant to be operated because they were designed sort of inefficiently from the get-go, and making them more efficient, bringing them to modern code, those kind of things. We've got a significant project. It's about an 8-year project. We're about a quarter of the way through, and we're seeing significant savings from these projects. And again, it may not look like we're doing a whole lot on this campus, but the projects are much more in depth and detailed when we go into the building. So it takes us a lot longer. We have about 8 steps within the stages of the retrocommissioning process. We've only got a couple listed here, but it starts with the essential monitoring and auditing and setting up sub-meters, really getting into the building science and understanding how the building is operating before we can go into the prescriptive stages of making changes and documenting and verifying and then following through. One of the most important pieces of the whole process is the training piece. We go in after we've done a building retrofit and we train the technicians that are operating the building as well as the building occupants who are living in the building on how to live in that building and how to work on it. So we're not defeating the purpose of the energy conservation measures that we've already put in place. This is an example of one of the projects we've done. Standard hot aisle or standard data center room center where traditionally you have your data servers in a large room. You're super cooling that room to make sure there are no hot spots and the servers can run efficiently. What we've done is we've physically segregated the hot aisle, cold aisle. So the servers only need cold air on their front end. They exhaust the hot air on the back end. So there's no point in cooling the back end of the servers. We physically separate those, only providing the cooling on the front end where it's needed. So that gives us significant savings just from a physical design perspective. We've modeled all of this, and so we're tracking it to make sure that we're doing the right things. And what we found is that we did the baseline. We were up at about 250 gallons per minute of chilled water. That's a sort of metric for how much energy we're using in that room to cool that room. We implemented the project of putting up those physical barriers, and we had as our predictive models, we sort of understood that if we did all those measures, we would be at about 50 gallons per minute from the savings. Well, when we implemented those dividers, we were only at about 150. Now, it's important to realize that because we studied that and said, well, something's wrong here. We're not getting the savings that we originally achieved or thought we would achieve. So we went back in and realized that the valves in that room were broken. The valves weren't opening and closing properly to supply that chilled water to the room. So we swapped out those valves, made that fix, and then boom, we were back at the post-retrofit, the predicted value that we wanted to get to. And that's critical because without that measurement and verification step, we would have walked away right here, said, good job, we did it, and we would have missed all the savings on the other side of it. So a critical piece of the whole process. This is a project we did in the Broad Center. At the time, it was the most energy-intensive building on campus. Proud to report it no longer is. In all cases, you can see the pre-retrofit numbers are indicated in the red. The post-retrofit are in the blue. In all cases, for all temperature ranges, the post-retrofit energy consumption is lower. So we've exhibited savings by swapping out mechanical systems and optimizing the mechanical systems in that building. And you can see here that baseline pre-retrofit, the heating, or I'm sorry, this is the cooling and the heating here have significantly reduced in the building, saving about $200,000 a year on an initial investment of $500,000 with a nice $240,000 rebate thrown in. So again, almost a no-brainer. I hate to use that term, but it really is at this point. This is another project in Downs Lauritsen with a building fan swap out. In the past, we had one fan in this building that was operating 24/7, 100%, just pulling air through that building to cool it, regardless of who was in there, what was going on, or what time of day. We've swapped that out with 3 fans. This is the pre-retrofit energy consumption of 1 fan. This blue here is the post-retrofit with 3 fans. What's important is obviously that's lower, so we've saved energy there. But it also fluctuates because it's a variable speed drive, so it modulates the fan speed based on the demand in the building. So we're not just cranking away 100% all the time, regardless of who's in there doing what at what time of day. This is a very interesting project that's actually going on here in the Beckman Institute. Beckman Institute is now the most energy-intensive building on campus, so we're attacking it very hard to make sure that we can change that. This is one of the ways we're doing that in one of the labs in room 244. We're putting in what's called a tech air valve. It's a low pressure drop valve, and essentially the way the old system worked is it relied on the pressure within the system generated by fan speed to open and close the valve that would then provide the necessary ventilation for fume hoods within the laboratories. This new valve that we're doing installing has fins, so it's independent of that pressure, so it can regulate the airflow to the fume hoods without any of that pressure. So that means that we can scale back the fan speed and change out to variable speed fans and significantly reduce the energy because we don't need that pressure to move the system around. So again, big savings. This is all being done in cooperation with the researchers in these labs, so it's absolutely critical that we're working with the users. I mentioned working with the users is very important. This is a screenshot of a dashboard, for lack of a better term, that we have for campus. And essentially what it is it's live on the website. You can go onto it and you can click on a building and find out real time how much energy that building is consuming at that moment in time. You can also then go and print out some charts and dig a little bit deeper into specific meters to understand more about that building. This is all designed to give the users information that they can then act upon to help us conserve energy, because obviously building users are part of the equation. So this is part of our education and outreach. I also mentioned we're working specifically with the technicians who are operating the buildings. And what we've done is we've taken reams of spreadsheet data that would make a lot of people go cross-eyed, and it would be hard to understand where the savings are. And we're converting it into a hot heat map that most people can figure out that this building here in the red is the building that has the problem. So it's a quick, easy way to identify it. That way, the technicians know that we've got a problem in this building. We need to go look at it even before we get a hot and cold call from the users or before we are wasting a lot of energy by overlooking it. We're also giving them training on how to make those changes once they're in the buildings, so they don't just put a Band-Aid on the solution, open a valve, for example, and everyone's happy because it's nice and cool in their room. But that's defeated the purpose of all the energy conservation savings that we've implemented going forward. So that was a whirlwind trip through energy efficiency. We're going to get into some of the buildings and renewable energy with Jim, and then we'll have some time for questions after that.
Great. Thank you, John. That was a great description about all the things we're doing to consume electricity or energy at Caltech, and Caltech has a huge appetite for energy because of the research. What I want to talk is a little bit about what we're doing in terms of our new LEED buildings. How many people aren't familiar with LEED? Okay, are not familiar with LEED? Okay, a few people. Okay, so LEED is a system that a nonprofit called the U.S. Green Buildings Council set up to give us a framework to make better decisions about designing and constructing more sustainable buildings. And so we use that system here at Caltech, and we have built several new, what we're called LEED certified buildings, and all 3 of them are gold. And so what we've done here is we've got Cahill, which was completed a couple of years ago. It is a LEED gold building, and the red is the modeled energy that the building was supposed to consume. And so one of the questions is, hey, it was supposed to do that, what is it really doing? And so what we can see here is the last couple of years, Cahill has been consuming just about what it had been modeled to do. We've done this with our other buildings that have been in operation for a couple of years, the LEED gold buildings, and they're all performing fairly well. There's a couple little hiccups, but we're working through that. So it's real important to go back and make sure these buildings are performing as they should. So I'll talk a little bit about what we're doing on the energy supply side. John talked about how we're doing to consume all this energy. And what we're doing to produce energy is, obviously we've had a cogen for a long time. Well, we have it. Yeah, there it is. Okay. So that's our cogen, which is basically a jet aircraft engine bolted to the ground, and it spins real fast. It generates a lot of electricity. There's a bunch of heat that comes out the back, and then we take that heat and we use it to generate some more electricity and to do some other things with it before we blow the gases up the stack. We're on our 4th generation of cogen here at Caltech. I say we're probably better at this than any other university in the country. They come and ask us for help with their cogen. But the cogen's great. It generates 60 or 70% of our electricity, but it's a single point of failure. If one little thing happens, this whole thing 12 megawatts goes offline, and then we've got to buy electricity for the city. So we're looking for other ways to generate electricity that are more reliable, maybe more economical. I mean, this thing burns gas, and that's great, but those that follow the gas markets know that gas hasn't always been $4 a therm. Sometimes it's been $12, and so we don't want to subject ourselves to that. So we've done a couple of other things. We've developed 1.3 megawatts of solar photovoltaic, and we'll walk by some of that today if you haven't seen it already. It's on the parking garages and many of the other buildings around the campus. You might say, why isn't it on every building? Because we've got a lot of fume hood stacks on our buildings, which get in the way of putting solar on every building. And we have a lot of beautiful trees. You know, trees are green, solar's green, but they don't get along. Solar doesn't like to be in the shade. So we did this through what's called a power purchase agreement, where we agree to buy all the electricity that it makes at a fixed price, and we don't have any capital in the deal. So we actually don't own these arrays. We lease the rooftop to a company who builds it, and then we buy the electricity. And we do that because we don't want to take capital away from research and education. We want to have cheap, clean, reliable power, and that's our goal. The other way we're doing that is with these things here that are called Bloom Energy Servers. Who's heard of Bloom before? Anybody? Oh, okay, great. Well, we got a whole, okay, well, that's great. So we've got 2 megawatts of the Bloom Energy fuel cells. Now, fuel cells have been around for a long time. Everybody in this room knows that. What's unique about these fuel cells is there's no heat recovery cycle. So most fuel cells that are commercially available, you've got to hook them up to a central plant. You've got to try to recover that heat, use it in an absorption chiller or something like that to make it efficient. But these are standalone. And if you put your hand right over the top here, and if you go back to the admissions house, you can walk right up to these, and you put your hand over the top, it's about as hot as a hairdryer. So all the heat is being consumed in the process. And so we also did these through a power purchase agreement. There's probably $15 or $20 million worth of capital here. None of it Caltech paid for. All we've done is agreed to buy all the power that it produces at a fixed price. If it doesn't work, we don't pay. So that's how we protect our risk. And the price we're paying is a couple of cents below the avoided cost of city power. So we're saving money from the minute we flip the switch. So what we wanted to do now is take a few questions that you might have about campus sustainability, and then I'm going to talk for a couple of minutes, orientate you to the Lynn Robinson building before we go on the tour, and then we're going to hear a little bit from Professor Tapio Schneider about the science in the building. But we probably have time for a couple of questions about campus sustainability.
Okay, we'll take questions here first. Can you comment about water?
Water, okay.
Yeah.
John knows more about water than I do.
We have a lot of projects going on in water. Obviously, it's an important part of the equation here in Southern California. We're looking at landscaping as a key indicator for our water. Even though most people assume that the landscaping on the campus is the largest consumer of our water resources, it's actually only about 10% of our total consumption. The vast majority is used in our central plant, which is fortuitous in some ways because every kilowatt that we save, through our energy conservation measures, is also gallons that we're saving through the plant operation. So they go hand in hand there. But we're certainly working on the landscaping because it is a visual component. And we'll walk by the Schillinger building today, see some of the landscaping there. The Annenberg building on the north part of campus is indicative of some of the drought-tolerant landscaping. And then clearly Lynn Robinson is sort of the cutting edge of our landscaping efforts, using and capturing rainwater to supply all the irrigation for that building.
In fact, we've reduced our irrigation water by about 25% the last couple of years. Yeah.
Hi. Yesterday we saw the solar decathlon people talking about how they were taking advantage of the interplay between the heating and the cooling. There are always things where you've got something hot that you want to make cold, and you have something cold that you want to make hot, and
Sure.
This has been known for a long time in buildings, but the two don't ever seem to come together. Have you found, is this a big deal, and are there opportunities to do it, and how difficult is it to actually arrange in reality to interconnect systems that are originally designed to do separate things?
Let me see if I can take a swing at that, and if I get it wrong, our energy manager, Matt's here, and he'll help me out like he usually does. But in the older buildings where you have what's called reheat, without changing out the whole building, it's very difficult to address. So a lot of times we cool the air down to get rid of the humidity, and then we warm it up to give people the comfort that they want for research. In the newer buildings, we found more efficient ways to do that. And you'll see some of that over at Lynn Robinson with what's called radiant beams, which are basically radiators. We're kind of going back to what worked pretty well 50 years ago. And then in some other buildings, like the Annenberg IST building, we're using what's called chilled beams, which is a device that's got chilled water or hot water in it. We blow a small amount of air over it, and so that becomes more efficient. So we're finding a better balance in the newer buildings and where we rehab the whole building. But in an existing building like this, where you have ongoing research, it's really, really hard to change everything out and not disrupt the main thing.
I think we have one more question over here.
Okay.
Yeah, I'm glad somebody brought up first. I was going to talk about it. I can't help but remember being in Gates and freshman chemistry and wanted a vacuum. We just opened the valve and ran sunny soap water down the drain. I'm presuming that you use vacuum pumps now. I've thought about this a lot of years as I walked past them. But one of the big battles the students had with buildings and grounds was we didn't like that ice plant. Well, now the ice plant's gone, you've got turf. I'm a master gardener in Nevada, and we are pushing people to take away turf and put in rocks, xeriscape. And the Southern Nevada Water Authority pays the person who converts $1.50 a square foot to take out the turf.
Right. Well, I guess I would answer that question with Caltech is a beautiful green place, and I don't want anybody to think that we're going to turn all the grass into rocks, because that's not our intent. And we do have a couple of places that I consider to be monumental lawns. And this is one of them right here. That will always be a lawn. There's a couple others that will always be lawns. But there are places where we have turf that we'd like to change it to more sustainable landscaping. And that doesn't mean rocks. That means some of the things that we're going to see at Schlinger and at Lynn Robinson that I think are very attractive, and I'd like to get your opinion. If you came to Caltech in 1930, you wouldn't have seen a lot of grass. So that's not something that was here in the very, very beginning. This, yeah, a lot of it was, yeah. Now this grass here, it looks like turf, but about 2 years ago, I mean it is turf, but 2 years ago we changed it out from the fescue to a much more drought-tolerant turf that uses a lot less water. So where we do have turf and we want to keep turf, we're making it more efficient.
Jim, do we have time for more questions?
I don't think so, because we need to pop through a couple more slides. There'll be a chance to ask your tour guides questions as we're going along. What I'd like to do now is just orientate you to the Lynn Robinson building before we get out of here on a tour. This is a building that we've been working on for the last 3 years. The senior project manager, Brad Smith, is going to be leading one of the tour groups. So if you get in his group, you can ask him all kind of hard questions. If you get in my tour group, go easy on me. But I think what's really amazing about this building is it's a historic building. There are 9 LEED Platinum laboratories in the country. They're all in new buildings, and this is the only one that's in an existing historic building. So we've preserved a part of Caltech's history. We've restored a building to its original architectural charm, and we've made it the most energy-efficient physical laboratory in the country. And you know, Caltech is all about first, and I think this is where we ought to be going. We've also used a lot of recycled materials and retained a lot of the building, so it's very sustainable. This is a celiostat where the 2 mirrors are. We may not get up there today, so I wanted to show you a picture of that. Here's the building here, and what's important and unique about this building is it has a solar telescope, and the solar tube goes all the way through 5 floors of the building, and then about 70 feet below the lowest floor is what we call the solar pit. And so this feature of the building, we decided to retain this feature, and we decided to use it to make the building even more sustainable. So today, as you're walking around, you'll see how we're going to use the celiostat to bring natural light down into the basement and some of these fiber optic fixtures. And then the part below the lowest floor we used as a storage pit for thermal energy storage. So we chill water at night up on the roof with radiant cooling, and then we store that water, and then during the day, I'll show you in the next slide. I should have hopped to this slide, I'm sorry. At night, we chill the water on the roof, we pump it down into this pit, and then during the day, we use that cool water to pump around the building in these chilled beams in order, or radiant cooling panels in order to cool the building. So that's one of the other unique aspects of the building. And I wanted to show you those before we walk through, because sometimes it's not obvious as you get into the building what those aspects are. What I'd like to do now is introduce Professor Tapio Schneider. Professor Schneider is the director of the Ron and Maxine Linde Center for Global Environmental Science. And although we build the buildings, he's the guy that does the work in the buildings. And so I wanted him to speak for a few minutes about the science that's going to go on in the building before we walk over there. So thank you for being here, Tapio.
Yeah, thank you all for coming. As Jim mentioned, I wanted to say a few words about a few specific laboratories that you will be able to see once you take a tour of the building. So in the Linde and Robinson laboratory, it is named in honor of Ronald and Maxine Linde, who donated funds for the renovation of the building and for the program. And before it was the Robinson building, it became the Linde plus Robinson building. Is what's called the Linde Center for Global Environmental Science. And what we do is ask fundamental questions about the environment. What we want to do is offer comprehensive, clear analyses of how the environment works, how it may respond to human interference, how it has been in the past. The kinds of questions we are asking, we as all the scientists in the building, there are about close to 100 scientists in the building, students and everyone included. For example, how has Earth climate varied in the past and how will it change in the future? We ask questions about what the relationship between clouds and climate is. They're very important feedback in climate change. The marine stratus clouds you see off Santa Monica, if you get fewer of them as the climate warms, it'll get even warmer. If you get more of them, they reflect sunlight, it won't get quite as warm, and the like. The question is, what do these clouds do, and we don't quite know. And these kind of very fundamental science questions is what we like to address. Other questions, of course, here in Southern California, we care about air pollution. How does smog form? What can we do to make the air even better than it already is? It's already much better than it was a few decades ago. What would be effective policies to make it even better than it is right now? And that's not always obvious. Just reducing all emissions is not economically feasible. It's not even necessarily scientifically the right thing to do. You want to ask, what pollutants do you want to reduce? What is most effective? The questions concern the carbon cycle. About half the carbon dioxide that's emitted by human activities ends up in the atmosphere, and the other half somewhere else. Somewhere else, we don't quite know where it is. It's taken up by the biosphere somewhere. We don't quite know where, and we like to figure out where it is. So these are the kinds of basic science questions we're asking, and I'll just introduce you to 3 laboratories where some of these questions are being asked and talk about some of the special features of these labs. So one is the laboratory of Jess Atkins. He's a geochemist who asks questions about past climates, and past climate years 10 to hundreds of thousands of years ago. And how you know anything about climate on those time scales is by looking at geochemical records. For example, the isotopic composition of stalagmites and corals that Jess and his group dig out from the deep sea. They bring them back to the lab, and then you look for tiny geochemical traces that can tell you something about the climate, the condition of the ocean circulation, and the like. In order to do that, often what you measure are metals, and metals in very, very tiny concentrations, which means you can't do this in any lab that has, in fact, any metal in it at all. You can't have a faucet, you can't have a hinge on metal, you can't have a screw, nothing. Because as soon as that's there, any little bit of corrosion that would happen there would completely contaminate all measurements. So there is a clean room, air free of particles. It's completely metal free, and you won't be able to go inside the clean room, but it has a little window, and you can look inside. There's a laboratory next to it where at least you can perhaps poke a head into the door. It's also completely metal free. And as far as energy efficiency is concerned, clean rooms are a big problem. They consume a lot of energy usually because you have to pump air through at a high rate to get the air clean, to filter the air. And this was one example where we thought long and hard about how we can build a clean room that not only is clean but also uses a lot less energy. And the design we came up with, and we realized actually a lot of people, there were engineers involved, facilities people were involved, but then also everything here happened in close collaboration with us scientists. Otherwise, you can't get the best design. That clean room, it uses only about a quarter of the energy of a typical clean room. So if you had built a clean room now from scratch, it would use 4 times as much, even a new clean room, than this clean room uses. And there are lots of little tricks about air handling and the like that make that possible. There's one lab that's also quite special. It's not in an energy saving sense, perhaps, but it's quite special in that it is what we call the quiet room among us. And the quiet room is a lab that is, in the lower left you see, this is copper. The lab is entirely a copper cage. Now you won't see this copper anymore. There's acoustic insulation on top of it, drywall and the like. It's behind it, but you'll be able to look inside. And why did we do that? Michio Okumura and a few of his colleagues, he's a chemist who does spectroscopy. He's measuring properties of gases, the optical properties of gases. And you need to do this at exquisite precision if you want to use these measurements, say, to calibrate satellite measurements of the composition of the atmosphere. If you want to figure out how pollution is forming in the atmosphere, you need very precise measurements of the composition of the atmosphere. And to be able to get those, you need very good knowledge and very precise knowledge of optical properties of a bunch of trace gases. And what we can do in this lab, it's a very unique lab. There are no instruments in there yet. We just moved in 2 weeks ago, and not all instruments have moved yet. But once this is up and running, it's probably will deliver the most precise measurements of optical properties of gases anywhere. You can measure properties of individual molecules. And it has all this insulation to get this high precision. You don't want any electromagnetic interference. You don't want any acoustic interference, vibrations, and the like. And this is as isolated a room as you can build in a building like this. So your cell phones definitely won't work. These are, in these two labs, we're asking basic science questions. There's some other labs where we develop technologies to solve a bunch of environmental problems. And in many technological challenges for the environment, you want to have something that works. But if you really want to make an impact on the world, not only for the virtue of saving energy, also just to make an impact, you want things that are energy efficient. Because in a lot of the developing world, there is no easy access to energy, water, and the like. And a number of us, Mike Hoffman, Rick Flagan, a few others, are developing technologies. For example, Rick Flagan is developing instruments to measure aerosols very quickly, very efficiently. These are these little smog particles just to make measurements of the atmosphere. They're developing techniques for removing contaminants from water. Clearly, access to clean water is one of the big challenges in the world, and they're coming up with ways of removing contaminants from water without using a lot of energy, and in particular by using sunlight to drive catalytic reactions with which the water can be cleaned. And in fact, one of the features I hope you'll see outside the Linde Robinson building, there's a very low-tech version of cleaning water with sunlight. There's a little fountain which isn't done yet. The rainwater that irrigates the landscaping, and that's also used to flush the toilets and the like in the building, you need to disinfect, and one simple way of disinfecting it is expose it to sunlight. So that rainwater goes through this fountain, is exposed to sunlight, goes back into the tank and into the toilet, and so forth. But of course, you want something more sophisticated for actually water that's a lot cleaner, a lot dirtier than rainwater. One other example, Mike Hoffman is working with funds from the Gates Foundation. It got some press recently that some people might have seen. He's developing toilets that are powered by sunlight, don't use any water. And that's clearly a tremendous public health benefit in much of the world if you can have sanitary conditions without using energy, except sunlight that you get for free, and without using water. And they're having some prototypes that are being developed in the lab. They're being developed in one lab on the ground floor that you'll be able to go through. And all of these techniques use sunlight. Where do they get the sunlight from in the ground floor here is slightly misleading. There's not actually a whole lot of daylight on that floor in the labs. They get the sunlight from the solar telescope. There's a beam splitter in the telescope that you'll be able to see. The beam goes into the lab, and they use the telescope for science in the labs. Jim mentioned a few of the energetic aspects of Linde Robinson. I think I don't need to dwell on that. You'll hear more on the tour, and Jim gave you already an overview. It is, as far as we know, the most energy-efficient science lab in the country. And Jim mentioned it uses about a quarter of the energy. It's 4 times more efficient than new construction would have required. If you compare it to typical lab buildings, it's about six times more efficient. It uses only 1/6 of the energy. And when we started this process, I should say, LEED is something that, in some ways everyone does on every campus. All the new buildings are LEED certified. And we started from the outset, said, well, LEED is nice. LEED is the standard of today, but what's going to be the standard of 20 years from now? That's what we want to build. And I think we succeeded. So you're in for a treat. You're the first non-construction and the like group of visitors to see the building, which means you'll have to put up with some construction still. There are still workers in the building today. You have to be a little bit careful, but I think your tour guides will guide you through. As I said, we just moved 2 weeks ago, and moving means there's still lots of boxes around, and laboratory instruments haven't all moved. So it's a sneak preview of what will be there in a few weeks. Thanks.